probability events involving the word and. Our objective, find the probability of one event and then a second event occurring. Notice I put the word then in parentheses. Oftentimes the problem will say just the word and, probability of A and B. And it does help to put the word then in there to recognize that you have two different things. One will precede the next. We're doing two events here. And the word then helps us to keep that straight. You'll see what I mean as I go through this video. Okay, let's recall what we know. We know the definition of probability, the chance that something, an event, will happen. We know that probability is always between 0 and 1. 0 or 0% means that the event is impossible. 1 or 100% means the event is certain. We know how to find the probability of an event happening. The denominator is the total number of outcomes that are possible, and the numerator is the number of ways the event you're looking for can happen. And we know that the notation, P parentheses with the event inside, says the probability of the event happening. Number 4 here, I want to remind you, because we're going to be multiplying fractions, that whenever you multiply two or more fractions, the result is smaller. When we looked at probability involving or, we expanded the possibilities. We expanded the chance of it happening. And so we added fractions because that was a larger fraction. As we look in this video at probability events that involve the word and, we are shrinking the chance of it happening. Okay, it's going to be a smaller possibility that it happens together than if they happen individually, and multiplying those fractions results in a smaller fraction. All right. So I had that stated right here. When dealing with the probability of an event happening and then a second event happening, again randomly, you're reducing the possibilities of success. You want to have two things happen. Okay, well that requires that they both have to happen individually, and that they in both happening, as they both have to happen individually, the chances of them both happening are smaller than they happen by themselves. Okay, let's take a look at an example here with pants and shirts, and then we'll do some examples and you'll see what I'm talking about. We got 2 pairs of pants, black and khaki, and we have 3 shirts. Okay, and let's say the black pants are in the closet and the shirts are in the drawer. Okay, so we're going to pick a pair of pants first. We have 2 things happening here. Pick a pair of pants and then pick a shirt. Okay, you don't pick them both at the same time. You do one before the other. We're going to do pants before shirt. So we have our black pants and we have our khaki pants. Okay, what's the probability of picking black pants? Probability of picking the black pants. Well, I have 2 pairs of pants and one of them is black. Okay, so when I select the pants first, the chances are that I randomly select a pair of black is 1 out of 2. Now I'm going to go to the shirts. If I selected the black pants, I can select either the white shirt, the red shirt, or the yellow shirt. If I selected the khaki pants, I can select either the white shirt, the red shirt, or the yellow shirt. So what's the probability of selecting the white shirt, independent of the pants? Selecting the shirt, in this case, has nothing to do with the pants. We're going to say they all match just fine. Well, I have 3 shirts, and the probability of picking the white one is 1 out of 3. Okay, so now, let's look at our outfits. If I select the black pants and the white shirt, this is the black-white outfit, black pants, red shirt, black-red outfit, and so on, black-yellow, khaki white, khaki red, and khaki yellow. Okay, so what's the probability? I select the black pants, I'll abbreviate pants PTS, And then I'm doing two selections, the pants first and then the shirt, and then the white shirt. Okay, well, let's take a look. I have 6 possibilities of a combination of pants and a shirt. One of those is the black pants with the white shirt. So the chance that I pull the black pants and then the white shirt, again, randomly without looking, is 1 out of 6. These 5 are what I'm not looking for. I want the black pants with the white shirt. Okay, so you can see here, if we take this fraction times this fraction, I get 1/6. So the chance of picking the correct pants is a half. The chance of picking the white shirt is a third. The chance of doing both of those things, I have to do this one and this one. Obviously, my probability gets smaller, and 1/6 is smaller than both 1/2 and 1/3. So the probability of the black pants and then the white shirt, okay, is equal to the probability of the black pants times, and I just goofed off how I was going to write the P, times the white shirt. Okay, well, the black pants is a 1 out of 2. The white shirt is a 1 out of 3. And there's the 1/6 that we came up with, okay, using our diagram and our understanding over here. Okay, so when you have more than one event, okay, we're going to be looking at you're doing things one after the other, more than one event. It's very important. Okay, the word and comes in with more than one event. And so we're going to use multiplication because when we have more events that have to take place, the chances of what you want taking place gets smaller and smaller and smaller. Okay, so we're going to use multiplication because multiplying fractions result in a smaller fraction. Okay, let's take a look at the 2 ways that you'll see and probabilities. Okay, the 2 ways are, let me get my sheet straightened out, okay, and probabilities come in 2 types. You have independent events and dependent events. Okay, independent events. As you might imagine, independent events that are not affected by the previous event. They are separate. Okay, for example, what happens first does not affect what happens second. In our pants and shirt example, you picked a pair of pants randomly from the closet, and then you picked a shirt randomly from the drawer. The shirt you picked randomly was not influenced by the pair of pants you picked in the closet. It wasn't like the number of shirts changed or anything or whatnot. Okay, so these are independent. You randomly reached into the closet, picked something, you randomly reached into the drawer, picked a shirt, and in fact, this happening had nothing to do with what you did here. Independent. How do we find that probability? Using and? Well, we just saw it. The probability of A and B is a multiplication of the two individual probabilities. The probability of A times the probability of B. Let's take a look at 2 examples. We're going to roll a single die twice. It has 6 sides, of course. Find the probability of rolling a 1 the first time and a 5 the second time. Okay, so let's look at this. We're rolling twice. We have 2 events happening. Okay, the first event is the first roll. The second event is the second roll. Okay, so I'm going to write this down. Notice the word then is not here. I'm going to write it down. So I want the probability of a 1, and then I want to get a 5. This and then tells me I'm going to be doing 2 things. Okay, well, what's the probability? Wait a second. Now, let's think about this. The second event rolling the die the second time has nothing to do with the first roll. The die is not thinking, hey, I rolled a 1 the first time, so I'm going to make sure I don't roll a 1 the second time. The die has no thought. The die is not influenced at all by the first roll. The second roll has nothing to do with the first roll. So these are independent events. So we're going to multiply the probability of a 1 times the probability of a 5. Okay, well, there are 6 outcomes, 6 sides on a die. One of those is a 1. Okay, again, there are 6 sides on a die for the second roll. One of those is a 5. So the probability of rolling a 1 and then a 5 is 1 out of 36, which is approximately 2.8%. Okay, so it's hard to do 2 rolls and to roll a 1 the first time and then a 5 the second time. For starters, your first roll could be a 2, 3, 4, 5, or 6. Okay, for starters, your second roll could be a 1, 2, 3, 4, or 6. So the chance of doing a 1 the first time and a 5 the second time is very unlikely to happen. There's a 1 in 36 chance of doing that. Let's take a look at the coin flips. Okay, here we want to take a coin and we want to flip this coin 3 times and we want to get 3 heads. Okay, so let's recognize we have 3 events. We have 3 flips. Okay, we're flipping a coin 3 times. So we're going to have those 3 different fractions. Okay, 3 events taking place. I don't even see the word and in here, but I know I'm doing it 3 times. So I'm going to say, this is probability, well, we want heads. First flip, heads. And then we want another heads. And then we want a third heads. Okay, so that's how it's going to look as I write it out with the P notation, the probability notation. And again, there's no word and in here, but we know we have 3 events and we're looking for these things to happen. And because it's 3 events, we know we're using the word and. Okay, well, this equals, okay, let's first think, does the second flip depend on the first flip? Is the second flip independent? Yes, it is. Okay, the coin doesn't think, I flipped ahead the first time, I better not flip ahead the second time. The second flip has nothing to do with what happened the first time. Same thing with the third flip. The third flip has nothing to do with what happened the second time or the first time. They're independent. So, multiply them. Probability of a heads times the probability of a heads times the probability of a heads. Okay, let's do them individually. A coin has 2 sides. One of those is a heads. Okay, the second flip, there are 2 outcomes, 2 total outcomes. One of those is a head. The third flip, there are 2 possible outcomes. One of those is a head. So what's the probability of flipping a head and then picking the coin up and flipping another head and then picking the coin up and flipping another head? Well, it's 1/2 times 1/2 times 1/2 or 1/8. In percentage terms, it's 12.5%. Okay, so these 2 examples are examples where these events are absolutely independent. What you did the first time has no effect on what you did the second time, which has no effect on the third time, etc., etc., etc. Now let's take a look at, as you might imagine, events that are dependent. Let me get my notes together. Okay, get myself straightened out. Okay, a slight bit more complicated. Dependent events, my paper's not even straight. Okay, dependent events are events that are affected by the previous event. What you did first changes what happens next. Okay, for example, what happens first affects what happens second. How are we going to solve these? Well, we're still doing more than one thing, so we're still going to use multiplication. So we solve these by multiplying the initial one, the first one, by subsequent probabilities that have been adjusted by what happened previously. With 2, probability of A and then B, we find the probability of A and we multiply that by the probability of B given that A took place, given what happened in A. Okay, so we're going to have an effect here that says you did something here that means that this probability has changed based upon what you did here. Let's use one of my favorite examples of probability, donuts, because I happen to like donuts. You have a dozen donuts. 6 are glazed and 6 are chocolate. What is the probability of randomly selecting a glazed and a glazed? So we're going to pick twice. Okay, so let's see. Select a glazed and a glazed. Okay, we have 2 events. Okay, so let me draw it out. Let's first make my fancy box. And let's put in a dozen donuts. Can you get any fancier than this? And we have 6 that are glazed, so I'll put the glazed in as G's. And we have 6 that are chocolate, so I'll do the chocolates as C's. Okay, so my question is, probability of a glazed and then, and again, that word then, we have and here, but the and then tells me I'm doing a second something, and then a glazed. Okay, well, the first one's easy. Probability of a glazed. All right, let's take a look. I have 12 donuts, and how many of those are glazed? 6. That was easy. However, now I picked a glazed. That one's gone. I picked it, I ate it. Okay, so now I want to select another glazed. Well, notice that the next choice is limited to these 11 donuts. This one's out of there. I picked it, I ate it. So not only do I have fewer donuts in total in this case, I also have fewer glazed donuts because I picked a glazed. Okay, so this is going to be times, this up here is times the probability the probability of picking a glaze given a glazed was chosen. Okay, let's write this down. Probability of picking a glazed given a glazed was picked previously. Okay, that's what this means. Your first event, you picked a glazed. Well, the second event has been altered because you took a glazed out. Okay, and so you've altered the possibilities of picking a second glazed. Okay, what happened? Well, you only have 11 donuts. This is 11 donuts remaining. Okay, out of those 11, how many are glazed? Well, 1, 2, 3, 4, 5. 5 are glazed. 5 glazed remaining. So this is a dependent situation because this second probability depends on what happens here because you took it out. Okay, so we do the math here. And this comes out to be a 5 in 22 chance when you multiply and simplify, which is approximately 22.7% chance of that happening. A little under a 0.25% chance, 25% chance of reaching in randomly and grabbing a glazed, eating it, and then reaching back in and getting another glazed. You got about a 23% chance of doing that. Again, notice the dependence. The first event affected the second event. Let's look at one more example. Okay. We are going to be dealt 3 cards from a 52 card deck. What is the probability of being dealt 3 kings? So let's recognize again, we have 3 events. We have 3 deals. Okay, so 3 deals. And we want to know, so 3 separate things. So the probability of a king, and then a king, and then a king. Okay, notice again, it doesn't say the word and. Okay, it did say the word and up here, but this one doesn't, but we have to recognize that we're doing 3 things, and so we have an and then an and then. Okay, so now let's think about this. Okay, so this is going to be the probability of a king. Okay, that's our first one. Okay, well, let's see. Let me get this one. I want to write how I want to do this. Okay, so that obviously, there are 52 cards. How many are kings? Well, there's the king of spades, the king of diamonds, the king of clubs, and a king of hearts. So there are 4 kings. Okay, so you got dealt a king. You have a 4 in 52 chance of that happening. However, you got a king. Now we're going to be dealt another card. Well, you've already been dealt one. That card's gone. Okay, so this is the next one is the probability of a king given a king was already dealt. Okay, all right. So we have a king given that a king was dealt. Well, we have 1 fewer card. I already gave you a king. Now I have 51 cards remaining. I have 1 fewer king. 1 fewer king. Okay, because I gave you a king. So the probability of the second one being a king is 3 out of 51. Okay, now I'm going to do it a third time. So the probability of getting a king given 2 kings. You got this one, and you got this one. So the probability of getting a king, given that 2 kings were already dealt. Okay, well, again, I go down, so I have 1 fewer here again. Because I already had 2 dealt, so now I have 50 cards remaining. And I have 1 fewer king. Which means I have 2 kings remaining. Okay, so the fact you get dealt a king here depends on the fact what was dealt here. If I gave you a king, if I gave you a king the first time, first off, I only have 51 cards left. Second off, I only have 3 kings left. On the third deal, well, I'm down 2 cards from the first 2 deals, and I'm down 2 kings from the first 2 deals. So I have a 2 in 50 chance of giving you a king on the third deal. Okay, let's do the math. This fraction times this fraction times this fraction simplified is 1 in 5,525, which, as you can imagine, is a pretty small percent. It's actually 0.2%. So the chance of you going to Las Vegas and the dealer dealing you 3 kings in a row is closer to 0% than it is 1%. Very, very unlikely to happen. That the dealer will simply take out 3 cards. Of course, the deck is shuffled, and you'll randomly get 3 kings, closer to 0% than 1%. So there you have it. And probabilities recognize that we're talking about more than one event happening, and that we're going to use multiplication.